questions though. You don't need to show your work. Just go ahead and write the answer for us. All right, good morning, everyone. Today is Tuesday, September the 28th. This is 2.05 day number 3. Don't forget, in class, I mentioned on Friday during both sessions that so Friday was 2.05 day 1, but at noon that same day, I had 2.05 day 2. Hopefully everyone listened to the recording on Friday, the 8:30 or the 10:30 class, and you remember me saying that. So if you haven't, go ahead and watch the noon recording of 2.05 day number 2. All right, so this is bell work. We have this piece right here times x, y. So I don't think I've talked, well, yeah, I did. So on Friday, the noon lesson, what is this matrix called? It's called the identity matrix. It is. It is. Now, something that you noticed, if you did the work, the identity matrix times this 2x1 matrix will equal that 2x1 matrix. So this 2x2 identity matrix times this 2x1 matrix will equal, well, itself. This is important. The reason why I'm doing this is because we're actually going to use this concept in today's lesson. So, I thought I used bell work to explain part of today's lesson. And then, here is the work if you really wanted to see what we did here, right? Everyone should have got X, Y. All right, who got this answer correct? Looks like everyone who's responded, or somebody, looks like some of you almost got it correct, right? I'm going to hope that those of you that did not get it correct, but almost got correct, they see the error of their ways, right? There's looks like 3 of you that almost got it correct. I trust that if you missed it, you see your mistake. All right, any questions on this bell work problem? Or did my work kind of answer it for you? Looks like we're good then. All right, silence. Silence means good, I guess. All right, 2.05. We're going to use the inverse matrices to solve systems of equations. All right, I need our paper, pencil, calculator, and then your prereq skills here. So we need to know how to calculate a determinant. We need to know how to calculate the inverse, and this was from Friday's lesson at noon, the recording, and multiplying 2 matrices. So, we're using everything we've learned so far in Unit 2 to do this lesson. If you don't know how to do a determinant, you don't know how to do an inverse calculation, you don't know how to multiply matrices, you can't do today's lesson. All right, solving systems. All right, so we have these 2 equations, 2 variables, 2 unknowns. And we're going to create or turn this system of equations into matrices. So we have the A matrix. This is the coefficients. So it's just going to be the 2x, the negative 2y, the negative 3x, and the negative 5y. So this is our A matrix. Now, this is an important page because we're going to apply this to every problem we do. So your A matrix will always be the coefficients, okay, the coefficient matrix. So we have an A matrix, we have an X matrix, and we have a B matrix. So every problem that we do will have these 3 pieces, the A, the X, and the B. All right, again, the A are the coefficients. Your X matrix will always be XY. So you're just going to have the variable X, the variable Y. So the X matrix will always be XY in a single column. So this is our variable matrix, XY. And then Our B matrix represents the constants. So we have -12 and 10. So again, your A matrix is the coefficient matrix, your B matrix is the constant matrix, and your X matrix will just be your variables, X, Y. It'll always be X, Y. But a question about would a three by three, or well, you mean a three? It would have to be a 3x4, right? A 3x4 matrix. If we had three equations and then three unknowns, so it'd be a 3x4. Would be the same concepts. Yes, it would, but we're not doing identity matrix with a 3x3 matrix. But yeah, it would be the same. Yeah, we don't do that in this class. All right, so that leads us to the setup of our equation. So here's the setup. So this is the setup for every problem that we do when we solve a system of equations by using the inverse method. Matrix A times matrix X equals matrix B. And don't forget, matrix A, coefficient matrix. Matrix B is the constant matrix. Matrix X is the variable matrix. All right, everyone good? I think more of you are just eager to see it actually in action, right? Like, once it's set up, what do we do next? Let's take a look. Well, after this slide, at least. Okay, matrix equations are no different, only the inverse is the inverse matrix. So I think somebody, I don't know, this class or another class asked, like when we solve equations, like, can we divide both sides by a matrix? Well, no, not really. But we can multiply both sides by the inverse, right? So if I said like 5x equals 10, all right, everyone can visualize that right down your paper. 5x equals 10. Mathematically, we would divide both sides by 5 to solve for x. But because it's a matrix, rather than looking at it as dividing by 5, we multiply it by its inverse. Well, the inverse of 5 is 1 over 5. So multiplying both sides by the inverse, 1/5, right? 1/5 both sides, you get the same answer, x equals 2, for example. Well, with matrices, same idea. If you want to get rid of this A matrix, you have to multiply both sides by its inverse. Now, remember, the inverse is not as easy as just flipping it like a number. 5 becomes 1 over 5. You can't do that with just a matrix. So we have to find the inverse of that matrix like we did on Friday. Sorry, my dog is barking at the wind. All right, so we multiply both sides by the inverse matrix. And again, we learned how to calculate the inverse this past Friday at the noon session. Okay. So when you multiply the inverse, remember the inverse times the original, you get the identity matrix, right? And we're going to see it in action. So kind of keep this step in mind. We're going to expand upon it when we actually do a problem to see what that looks like. Oh, also note, I should have really highlighted this. When you multiply both sides by the inverse of the matrix A, it must be to the left. So the inverse is to the left of matrix A, and the inverse is to the left of matrix B. That is super important. Super important. Remember that. Write that down. So when multiplying by the inverse, it must be to the left on both sides. Let's see it work. So we got these 4 problems here. I'm going to have these 4 on their own page, so don't worry about writing these down right now. All right, first one. So you can kind of see based on my blue boxes that there seems to be a lot of stuff we have to do, right? So I have it divided into 2 parts, separated by this little red divider here. So on the actual, in this box here, this is where we actually have the equation set up, right? Remember, matrix A times matrix X equals matrix B. Remember that? Remember that equation we just went over a few slides ago? So this is where we actually do the equation to solve for the answer, X and Y. On the left here of my divider, this is where we have to do our setup. Like, in order for us to actually solve this, we have to know what matrix A is. We have to know what matrix X is. And we have to know what matrix B is, right? And we also need to know what the inverse matrix of A is. So that's why I have them already set up here. So we have to know A, inverse A, and X and B. Don't remember, matrix X is just XY. It's always going to be XY, no matter what. Matrix A, these are going to be our coefficients, -3, -4, -2, and 5. Matrix B is the constant matrix, so 0 and -23. All right. So we pulled out A, B, and X. And now we have to calculate the inverse matrix. Remember doing that from Friday. All right. In chat or on mic, what do we do first when we find the inverse matrix? Find the determinant. Yeah. So we have to, absolute value of A. Yeah, and determinant. We need that first. So we do that, right? Give you a moment to see if you can quickly find it. Anybody have the determinant of matrix A calculated? -23 is what, yeah, so -23. I agree with you. I think that sounds right. So there's our setup, and there's my work in the -23. So I trust all of you can find the determinant of your matrix A, so I'm not going to spend any time on it. But all of you should be able to get -23. And then to actually calculate the determinant, it's 1 divided by the determinant multiplied by the matrix, but we have to do stuff to this, right? Remember from Friday, we have to swap these 2 diagonals, right? So this 5 gets put top left, this -3 gets put bottom right. These elements don't, they stay in the same place, but we have to just flip the sign. So negative becomes positive and negative becomes positive. And then we have to multiply it, right? And then don't forget to simplify if we can. It looks like everything is simplified. And yes, when you find the inverse matrix, more than likely you're going to have a matrix full of fractions. That's just the nature of it. Really can't get around that. I would be surprised if your inverse matrix did not have fractions. But it's possible that it won't. Like, there are situations, of course, where you'll have just integers, right? Okay, so we have everything we need to actually solve this problem now. We have matrix A, we have the inverse matrix, we have matrix B, we have matrix X. So all we're going to do is set this up. So we're going to replace A with, well, what A is. We're going to replace X with, well, what X is. And replace B with what B is. So there is our first step in part 2 of the problem. Okay. And you know, the nice thing about these problems is every problem is done the exact same way. Exactly the same way. You know, your math will be different, of course, but every step, every problem that we do using the inverse method to solve a system is going to be the same. All right. Next. Now we want to solve for x, y. So basically our goal is to get this by itself, right? So let me jump in towards the end here, but that's our goal. You know, I think it's important for us to know, like, what are we trying to get to, right? And we're trying to get to the variable matrix xy is equal to some other 2x1 matrix. That is our goal. All right, so think of, you know, math, right? So how can I get rid of this matrix A? So this is matrix A times matrix X. How can I get rid of matrix A? Multiply by the inverse. Yes, so we're going to multiply by the inverse, left side and right side. Remember, but it has to be, when I multiply my inverse matrix, where does it have to be on both sides? To the left of everything, yes. So we multiply the left by the inverse and the left by the inverse. So here's a question for you. When I multiply this matrix by this matrix, do I need to show any work, or can I go right to what the answer is? And if so, like, what is the answer? Well, we don't need to see if it's an inverse. Like, you know, Simon says, you know, if we need, you know, you need to see if it actually is the inverse matrix. And yes, you know, we could multiply this out, right? We could to check our work, sure. Or we can just totally trust that we did this correct, right? So we don't have to, but it would be nice to show the work, right? Now, what is the inverse? So remember, this is the inverse A times A. Whenever you multiply a matrix by its inverse, what will it always equal? Yes, it will always equal the identity matrix. Yep. Yeah, you can. So Noah says, oh, sorry, not Noah. Naomi says you can go right to the answer because a matrix multiplied by its inverse will always be the identity matrix, and she is correct. Yes. So the inverse of A times A will always be the identity matrix. And remember from bell work, right? Whenever you have the identity matrix times, well, a 2x1, it's always going to be equal to the 2x1. So I really don't even need to show this per se. I could just really just kind of cross these off and carry down my XY, right? But I'm just kind of showing this for completeness. If guys, so this right here, this is a TGA problem. This is TGA number 3. You'll have to do this problem, which is really not that bad. So TGA number 3, if you showed your work in your setup, you did this, and then you went from this step here down to this right here, and you didn't show the identity matrix, I'm okay with that. Hopefully that's clear. So if you want to go right from this times this times this right to just your variable matrix, that's fine. Doesn't bother me. I'm just showing it for completeness. This times this identity times this 2x1 will just equal the 2x1, just like on bell work. Now, we do have to multiply this matrix times this matrix. So I'm going to give all of you like 2 minutes, right? 2 minutes should be enough. Multiply this matrix times this matrix. Give all of you 2 minutes to quickly do that. Ready to go. And remember, we can do, remember it's, ooh, I better use a different color besides blue. Maybe use green. I don't know. So remember, it's the row times the column, right? And this is a 2 by 2 times a 2 by 1. By the way, your final answer for x and y will be a nice integer, no fractions. So if you solve this problem and you get to 2 nice integers, you probably did it right. So Enzo put a message I just read just now. He probably wrote it a few minutes ago. The identity matrix is the matrix equivalent of 1 then. I would say that's probably true, yes. Yeah, I would say that's probably true as long as the it has, so as you're solving this, let me go back and, there's always an if, right, or a but. So going back to this, so yes, I think it's safe to say that the identity matrix is the equivalent of multiplying a matrix by 1 if the dimensions are correct. So, this is going to be, let me go ahead and write this on the screen here. This is a 2 by 1. Or sorry, this is a 2 by 2. Uh-oh. My touchscreen's not working. Ah. Two by 2, and this is not the worst mouse handwriting. So yeah, as long as obviously, these have to match, right? And then the answer, the 2 by 1, needs, oops, the 2 by 1 needs to be the same dimensions as this second matrix. So I guess those are the conditions, right? 1, they have to be able to multiply together, and 2, the solution must be the same dimensions as the second matrix dimension. But just for simplicity, then yes, identity matrix is the equivalent of multiplying by 1. Okay, so what is the answer in ordered pair form, x comma y? 4 comma negative 3? Yeah, 4 negative 3. Nice job. Here's the math if you do want to see it. Negative 5 over 23 times 0 plus negative 4 over 23 times negative 23. That's for the first row. And then the second row, we remember we got to shift that down. So we have negative 2 over 23 times 0 plus 3 over 23 times negative 23. And I trust everyone at this point is pretty good about multiplying matrices together. If you're not, you should probably really spend time on it. because this is kind of a very important piece in unit 2 to be successful, right? I feel like we multiply a lot in this unit. All right, so let's recap this problem. All right, so we have two parts to this problem. We have part 1 and part 2. Part 1 is purely just finding your matrix A, your matrix B, your matrix X, and your inverse matrix. So that's part 1. We have to find those 4 matrices: matrix A, matrix B, matrix X, and the inverse matrix. The inverse matrix, obviously requires some work. We have to find the determinant to begin with, and then we have to, do what we did on Friday at noon to get that answer. All right, so that's part 1. Part 2 is, well, the setup. And every problem is going to be A times X equals B. This is just always the way it's going to be. We replace these with what A and X and B are equal to. And then from this point, this is where the solving actually starts. We have to get rid of this matrix A by multiplying both sides by the inverse matrix. These more or less cancel out to become just the matrix XY, right? But there's the math, or this is what actually is going on. This times this is the identity matrix. Identity matrix times this 2 by 1 is just equal to, well, the 2 by 1. We did that in bell work to show that. And then on the right side, this is really the only math that we have to do, right? This, well, other than part 1. This is, in this problem, this is the only hard math in part 2. This times this, plus this times that. First row, this times this, plus this times that, second row. And, we simplify, and you should get 4 in the first row element and -3 in the second row element. All right, how's everyone feeling about using the inverse method to solve for your systems of equations? Lots of steps, but not too bad. We've done worse, right? Yeah. Let's look at another one. All right, remember we got 4 examples, so here's our third example. So let's everyone do part A, or not part A, we'll say part 1 of this problem. So this is part 1. This would be the actual part 2. Some of you may actually skip the setup, and maybe a lot of you will just go to, we'll say xy equals the inverse. So really, the answer is going to be the inverse matrix. Let me get my pointer out here. The answer is going to be the inverse matrix times your constant matrix, right? That's really what we're going to, right? So maybe some of you will just skip this setup. On your TG, I do want to see it though. I do want to see these first 2 set up. None of you should just go right to, even though it's what it is, right? It is what it is. It's the inverse matrix times your constant matrix. That's really what we're doing. All right, so everyone should have easily gotten those 3 things, right? How did everyone do on those 3? 100%, I hope, right? All right, so I'm going to give you all 1 minute to calculate your inverse matrix. Ready, go. right. All right. Inverse matrix. Well, what's the determinant? Let's start there. What is the determinant of matrix A? Negative 27. Yeah, I agree with that. Negative 27. So then everyone should have got that, right? And then by multiplying, and don't forget, we have to simplify too, right? On your TGA, you should simplify. If you don't, I will mark things wrong. So in my eyes, if I see that you don't simplify your answers, you're not done. If you're not done, you don't get credit because, well, it's wrong. All right, how did everyone do on the inverse matrix? Like most of you did really well. Looks like one person looks like they got most of it right, and they made maybe a small mistake, or maybe they just didn't reduce, right? All right. So Noah says, for the TGA, do you want the negative sign in the numerator? It doesn't matter to me. Um, so I personally prefer it in the numerator. That's where I like to see it. If you want to put it out in front, that's fine. One place where you can't put it is your denominator, right? So even though it's down here, do not put that negative in your denominator. Never. I would say it's a general rule you don't do that. I know the modules definitely mark it wrong if you do that. Also, let's say one of these was negative. So let me go back to like this right here, right? So 1 over negative 23 times negative 3. If you put a negative 3 over a negative 23 and that's how you leave it, I will mark it wrong because a negative divided by a negative is positive, and that's how we got a positive right here. So keep that in mind, right? Um, so yeah, I don't care. Answer that question. I don't care if you put a numerator, and I don't care if you put it out in front. I do care if you put it in the denominator. Don't do that. All right. So going to part two, right? We have this setup. Like I said before, like every problem is going to be the same. So really, we know that we're going to have the inverse times the constant matrix, right? So yeah, we that's what we really care about, right? That's really the whole point, is to do the inverse matrix times the constant matrix to get our answer. But I still want you to show the setup. So, we're going to have that, right? Multiply both sides by the inverse. The inverse times the actual original matrix is just the identity matrix, which you don't have to show this. If you just go right, this times this is equal to this, you don't have to show this. I don't care to see that on TGA unless you want to show that. Doesn't matter to me, because in the end, this times this is just itself, right? So yeah, I don't care. All right, so I'm going to give you another, let's say another minute. One more minute to actually finish the problem. So multiply this times this. All right, what is the answer? X comma Y. Ordered pair form. 2 comma 2. Anybody else? 2 comma 2. Some of you may still be finishing the problem, and that's fine. 2 comma 2. So we got 2 people that say yay. All right, we got a third confirmation, 2 comma 2. All right, we got a fourth confirmation, 2 comma 2. I also agree. It's 2 comma 2. All right, let's just see the actual the math. Hopefully all of you in this class have a calculator that is not on the computer that you can actually physically type on, and your phone doesn't count. And hopefully that calculator does fractions. And when you do fractions, hopefully it gives you the answer in fraction form. But in this case, it actually ends up just being 2 nice integers. But nobody in pre-calc should be using their calculator on their computer. You really need to have one separate. I like the FX300. I like the FX115. Those are the two that I like. They're $10 for the FX300 and $15 for the FX 115. More than enough to do very well in this class this semester and next semester. You will definitely need it next semester. So if you're kind of really using the computer to do all your work, next semester, you're going to have a heck of a time doing well in the class because you really need one to switch between degrees and radians at a push of a button. Because remember this unit right here, this is the pre-calc semester. A lot of numbers, right? Next semester, starting in January, it's all trig. There is calculations algebra based stuff that we're doing now, but most of it is trig, like unit circle stuff, degrees, radians, lots of sine, cosine, tangent is part of it, but there's hyperbolic sine, hyperbolic cosine, hyperbolic tangent, inverse stuff. There's a lot that you really need to have a separate calculator for to be successful. So you should get one. Long story short, get a calculator. All right. All right, everyone do this one. I'm going to give all of you, I think 5 minutes might be enough to solve this problem. Say 5 minutes. Ready, go. And when you are done with this problem, I want you to choose choice D as in done. When you are done with this problem, choose choice D as in done. And it'll let me know if you're done. So within 5 minutes, if all of you are done, we'll just go on, right? 5 minutes. It can be a fraction, sure. But I can tell you right now, the answer for this problem is not a fraction. All right, so it looks like a majority of you are finished. There's still like maybe 3 of you that are still working on it, but let's see what's going on. I think some of you might be stuck, it looks like. So that was 10 minutes. All right, so everyone should have had these, right? So all right, everyone do good on part 1 of the problem. The crucial piece is your inverse. If your inverse is incorrect, your answer will be incorrect. So this right here pretty much determines if you'll get the answer right or wrong, right? So you have to be very careful when calculating your determinants and make sure you know how to set this up, right? Remember, the diagonals trade places. And then these diagonals, they don't trade places. They stay the same, but they flip the sign. So this 5 becomes -5. That -1 becomes +1. So you have to know how to do the inverse properly. So I'm guessing the 3 people that didn't quite finish, they made a mistake somewhere, right? Was it here? Be my guess. Yeah. Do you see your mistake? What you forgot or what you thought, what you wrote down? Maybe you wrote it down wrong. Okay, yeah, as long as you recognize the mistake you made, and hopefully you don't make that one again on future problems. That's the whole point of doing these in class together, right? Anybody getting a lot of like spam calls the last like couple weeks, like a lot more? I know I am. So much more. All right, so anyway, looks like a lot of you put the answer in chat, 0, -0, -4. That sounds right. 0, -4. Yeah, I agree with that. So let's go to the setup, right? Did anybody make the mistake? So did anybody make it this far, but their mistake was multiplying these two together? Anybody want to fess up to that? So I'm guessing people who did not finish made their mistake when doing the inverse. All right. All right, how's everyone feeling about using the inverse method to solve a system? Pretty good. Just got to be careful, right? Take your time, double check your work. All right, so we have like 3 minutes left. We don't have time to go through this last one, which is this one right here. So go ahead and everyone write this down, and they can do that on their own. -4x equals -12, and 3x plus 2y equals 5. Any ideas on what we should do for this problem here? Placeholders, yeah. So there's your hint, and it'll say use a placeholder. So we're missing the y. So make sure you put a +0y in here. So when you actually set up your A matrix, your B matrix, and your X and your so forth, that you have that in there. The nice thing is, really, could we solve for X really quick in this first problem? Yeah, so we know that the answer should be +3, right? So your final answer, X, should be +3, but let me come back to this page real quick. All right. So kind of final thoughts on system of equations. All right, so we know we've learned since beginning of our math careers in grade school, we can solve a system of equations by graphing, substitution method, elimination, also called linear combination method, row echelon form, all right, or reduced row echelon form, REF. That's going to be your TGA number 1. Will be that one. Using Kramer's rule and using the inverse matrices, which is today's lesson, and that is your TGA number 3. I did a 3x4 RREF problem with one person last week, and I forgot what day it was, but you want to check your recordings on every day last week, and sometime, I don't know, it was like 1 o'clock or 2 o'clock, I did one. It was like an hour long. I did it. You really probably want to watch that recorded session that I had on working out a problem that's a 3x4. Yeah, so let's go back to, and real quick, this page. So basically, we know all these methods, and what we could do, we could actually use one easy method to solve to get X and Y. So that way we actually know what the answer is supposed to be in the end. And then, like for the TGA, if we know what the answer is supposed to be, we can then work it out the way that the problem was intended. So like I said, if you don't like the inverse matrix method from today, do a different method to first solve for X and Y, so you know what the answer is going to be, and then actually work it out. And then if you finish the problem, you get down to the answer, you got it right. Same thing goes for like REF or Kramer's rule or whatever. But going back, yeah, so like this problem, we could solve for X real quick, and once you have X, plug it into this, right, substitution method, and then you can solve for Y. So at least we'll know what the answer is going to be, right? So if X is 3, you plug 3 into X, that's 9. 5 minus 9 is -4, divided by 2 is -2. So Y is -2. So just showing so we know the answer is 3, -2. We know that should be the answer, and by using this method, we should get to that. So please work out this problem on your own, and then make sure you get down to the correct answer. Other than that, everyone, looks like time is up. So as always, thanks for coming, and I hope you learned something. I will see you all tomorrow. I think tomorrow is our unit review. I think that's right. Yeah, we're doing our unit 2 review tomorrow, and then your test will be on Thursday and Friday this week. Wow, we're just chugging along. And then I think we're doing our midterm review and final test your midterm review and the midterm test on next Monday, the 4th. All right, I'll see you all tomorrow.